So the only thing I could think to call this lesson was building Maclaurin series from others, which means how can we use the three series that we have memorized to cut down the work we have to do for other ones? So for instance, I might ask a question like, let's see here, find a Maclaurin series for the function e to the x squared, right? Now, the first thing I want to mention to you is you need to be thankful for how marvelous this lesson is, which sounds funny. But the idea is, think about how bad that would be to do by hand. Think about the process of having to take that function and take its first derivative and second derivative and third derivative and fourth derivative, and then plug 0 into all of them, and then plug it all into the Taylor-Maclaurin series formula and work through all of that. What I'm going to show you here, I'll be able to fit on this page without even having to scroll down, I don't think. And what we're going to do is we're going to start with, well, what is e to the x? What's the Maclaurin series for e to the x? We memorized it in the last video. We learned it in the last video. 1 plus x squared over 2 factorial plus dot 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 plus x to the nth over n factorial, dot dot dot. So if that's e to the x, then how could I get e to the x squared? Well, I could get e to the x squared by simply plugging x squared everywhere I see an x in that series. So 1 plus x squared plus x squared squared, that's x to the 4th over 2 factorial. The next one would be x to the 6th over 3 factorial. I didn't write that one up here, but I'm just writing another one so you can see it. Heck, we could even figure out what the nth term is, and you don't even have to try and find a pattern here. If you know what the nth term is here, just plug in x squared there. It's going to be x squared to the nth. Well, wait a minute, we can do better than that. X squared to the nth is, you can multiply those powers. That would be x to the 2n over n factorial. And there you go. Maclaurin series for e to the x squared. Like, this is supposed to be shockingly, amazingly, awesomely fast and simple, right? And the reality is that, in as far as I can tell, the majority of questions asked on the AP exam about this kind of stuff are this kind of thing. They're not going to ask you to take 5 derivatives and plug things in and find the 4th degree polynomial. They're going to say, well, if you already know what e to the x is, then tell me what e to the x squared is. Another example, I think I've got 2 more examples planned for this. I might go on and do another one. Another example of that would be something like, what if they ask you to find a Maclaurin series for the sine of x cubed? And I would really recommend it. It doesn't take a long time. Take a minute, pause your video, and do this one. I know you don't have it memorized yet, but look back in your notes. Figure out how you would get sine x, and then how you would get sine x cubed from that. So if you want sine of x cubed, I think your best bet is to sort of start with what sine x is. Until you have them memorized, until they're really, really clear to you, write this down. Sine x is all the odd powers. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus, and then we had negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And then there's a plus dot 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 on the end. I suppose I could even scroll sideways and do that, because it does continue on forever. So now when you plug in the sine of x cubed, well, I'm just going to plug in x cubed. This will be x cubed minus x to the 9th over 3 factorial plus x to the 15th over 5 factorial plus, let's see, this will be negative 1. And here's where it gets a little bit funky. This is negative 1 to the n. When I plug in x cubed here, I'm going to end up with, and I'm going to sort of write it down below, x cubed to the 2n plus 1. So we might choose to write that as x to the 6n plus 3. But the denominator is still 2n plus 1 factorial, right? And I mean, like, be astonished, be amazed. Here it is. This is the, I mean, no joke, this is the 15th degree Maclaurin polynomial for the sine of x cubed. And that's, I mean, I'm sorry, but my breath is taken away. And we can even go one step further than this. I mean, let me, and I don't want to make too much work for you guys, but what if a problem had asked for x squared times the sine of x cubed? I mean, talk about problems you don't want to do the long way. Imagine having to take multiple derivatives of that thing with all of its product and chain rule glory, plugging 0 into it all along and trying to use the Maclaurin or Taylor definition. The easier way is to say, look, if I already knew what sine x was, I could figure out what sine x cubed was. Once I knew what sine x cubed was, I could just multiply it by x squared. Like, understand, this sine x cubed is just this. And so if I just distribute x squared through this thing, I'll get what this is, right? So this is going to be equal to, this was x cubed, so when I multiply by x squared, it'll be x to the 5th minus x to the 11th over 3 factorial plus x to the 17th over 5 factorial plus negative 1 to the n. Now, think about this. What happens to this power of x when I multiply by x squared? If I have x to the 6n plus 3 times x squared, I should be able to add those powers because they have the same base. This will be x to the 6n plus 5 all over 2n plus 1 factorial. And this is a big part of today's lesson. I mean, really, this is the heart of today's lesson. This idea that we don't have, like, unless it's necessary, you don't have to do these problems the long way. You can use composition to plug things in. You can distribute things through them. You can even divide. And I think that's the last example that I had prepared for you guys was this one. What if I asked you to find a Maclaurin series for the cosine of 2x minus 1 all over x squared? If you feel like you're up to it, I'd recommend pausing this and trying this out on your own. What I'm going to do is I'm actually going to give a hint right here. So I'm going to sort of give the walk through the problem and then let you do it on your own if you want the hint. So the hint is think about how are you going to do this Maclaurin series-wise. What we should do is take cosine and plug 2x into it. After you're done with that, take that series and subtract 1 from it. Once you have that series, divide the entire thing by x squared. And if you do that, you will get the Maclaurin series for this entire thing. So like I said, try that on your own. I'm going to run through it right here. So I always recommend starting with what the base series is, unless you know for sure that you know what it is. So cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. I'll go ahead and put down the x to the 6th just because I want to. This is negative 1 to the n, x to the 2n over 2n factorial. So that's the base function, the base power series. So the next thing I'm going to do is I'm going to plug in 2x to all of these x's. So now I have the cosine of 2x being 1 minus, and I'm kind of inclined to not even multiply that out. Like, I think I'm just going to leave this as, well, no, I want to do a little bit better than that. I think I could do like 2 squared x squared over 2 factorial plus 2 to the 4th x to the 4th over 4 factorial minus 2 to the 6th x to the 6th over 6 factorial. Now, on yours, you may have done 4x squared and 16x to the 4th and 64x to the 6th, or you may have just left it as 2x squared, 2x to the 4th, 2x to the 6th. Those are all fine. Those are all just simplifications. At the end step here, I'm looking at negative 1 to the n, running out of space here, negative 1 to the n, and then it was basically 2 to the 2n and x to the 2n all over 2n factorial, right? Now the next step is that I'm supposed to take that thing and subtract 1 from it. So what happens if I take this entire thing and subtract 1? Well, won't it just remove that piece? Won't it be true that the cosine of 2x minus 1 is just all of these terms? Negative 2 squared x squared over 2 factorial, plus 2 to the 4th x to the 4th over 4 factorial. In the interest of space, I'm going to leave this one off, but know that it's there. Minus ... plus negative 1 to the n. And if you think about it, subtracting that off doesn't actually impact the nth term. It just impacts where the thing started. Now the last step in the process, how am I going to get this whole thing? I will divide this entire thing by x squared, which just means I'm going to drop the power of all of the x's by 2. So, cosine of 2x minus 1 all over x squared will be, when I divide this one by x squared, it'll be negative 2 squared over 2 factorial. Dividing this one by x squared will give me 2 to the 4th x squared over 4 factorial. If you were following along, this one here would be 2 to the 6th x to the 4th over 6 factorial. Again, in the interest of space, I'm going to leave that one off. And my nth term, does doing that impact my nth term? It does, because doing that happens to every term. Unlike the 1, which only happened to the first term because it was subtraction, this division by x squared is going to impact every term, including the last one and all subsequent terms, right? So it doesn't impact the power of the 2, but it does decrease the power of the x by 2. We divide by 2n factorial. This is that power series. And I mean, if you were convinced before about how great this is, think about this. Imagine having to take multiple derivatives of that to try and find the Maclaurin series. That has every problem built in, a quotient rule and a chain rule, and that's only for the first derivative. Who knows how bad it gets after that. There are some more things that can be done with this that I'll show you in the next video. I'm sorry this one was so long, but I'm hoping this makes sense, and I'm hoping you guys get it and that you'll enjoy the assignment.